Thanks, Anna, and I hope everybody knows there's going to be a multiple choice exam at the end of this. Next up is Andrew's Scrogings, and Andrew's going to put us into context about what good graphite looks like, what bad graphite looks like, and what some of the other graphites look like. So I'll hand over to Andrew. Thank you.
John, thank you very much for the introduction. And thanks all for your time. I'm going to share some ideas and observations I've made on natural graphite geology. The overriding theme will be not all graphite is created equal, and that leads through to the good, bad and awful, which we'll have a look at in some thin sections down the microscope a bit later on. The outline: what is natural graphite? Something about the flake graphite geology, not all created equal, and then the good, bad and awful we'll have a look at under the microscope. And now I've done it again. What is natural graphite? Graphite is made from carbon. It's unusual in that it's a mineral, it's an element as well as a mineral. It's very soft, as we all know. It's flexible. It exhibits both metallic and non-metallic properties. Metallic properties include thermal conductivity, and non-metallic such things as lubricity. And natural graphite occurs in three main forms, certainly as far as commercial sales go. Flake graphite, which is the biggest market, then amorphous, and then vein graphite. And there are samples at the back there if any of you want to have a look at them. And these three types of graphites find different markets, sometimes overlapping, but generally different market applications. And we'll be hearing from Daniel later about the processing of flake graphite, but essentially the flakes have to be, and this talk's going to focus on flake graphite, are extracted by crushing, milling, and then flotation. And it's pretty obvious that extraction by crushing and milling is very likely to reduce the flake size. And that's where the original quality of the material counts for a lot, and the quality of the product you're going to get out. And some process easier than the others, and one of the really good examples is from Black Rock, who've managed to get over 99% with a very simple flow chart. High purity and maintain the integrity of the flake size distribution. Just to have a quick look at what they look like, this is a high-grade graphite sample from Germany. These silver areas here are the graphite from an underground mine. It's also mined underground in Sweden, in Norway, and I've got a sample of the Norwegian stuff at the back. That's amorphous graphite, which is metamorphosed coal. It looks like coal. China's the biggest producer. And then vein graphite, where we have veins of graphite cutting across granite, and that's a small but specialized market. We don't need to read all the details on these, but what I'd like to highlight are these pictures here of spherical graphite and expandable graphite. And that's the hallmark and the reason we need flake graphite, because it's the one type of graphite that can be used to make these forms, which are used in batteries and battery anodes. These here, that's a plant for making spherical graphite in China. And then we have amorphous graphite that's used mainly in the steel industry for adding carbon to steel, also used in coatings and foundries and sometimes for pencils. And the price is a lot lower. That's one of the reasons people use it. It's also been substituted to some degree by coal or anthracite, roughly $300 or $400 a ton US, compared with anything between roughly $700 and $2,000 a ton for flake graphite, depending on the quality. And then currently the most expensive graphite, produced about 5,000 tons a year, is vein graphite from Sri Lanka, and is used in many specialist applications, such as the carbon brushes for electric motors. You know how many servo motors cars have in these days, and a lot of it goes into that. And that typically sells for around $2,000 a ton. Flake graphite geology. Flake graphite occurs in rocks known as gneisses and schists, metamorphic rocks. They're formed by the heat and pressure. As a rule of thumb, graphite flakes, and again I'm focusing on the flakes, increase with increasing temperature of metamorphism. Another thing to note is that flake graphite varies both within deposits in size and character, and from deposit to deposit, so they are not all the same. There may be more than one flake population within a deposit. You could find one layer of rock that's got a whole lot of small flakes and maybe some bigger ones, and that impacts on the processing and what you get out of it. Important thing to note is the in situ flake size. You may have seen this reported, especially in the early days of the people chasing graphite, that they reported on in situ. That may or may not reflect what you can get out of the rock, so you've got to be very careful of that in situ flake size. And then on top of all the variables with the heat and pressure and temperature, there's the weathering of the deposits, so they get weathered by rain, sun, the rest of it. Sulfide minerals like iron FeS2, iron pyrite, fool's gold, become rusted or oxidized, so that affects the deposit. And silicate minerals like feldspar turn into clay, which also have an impact. We'll have a look at some photos later. And then we may get secondary minerals, and there are cases in places like Australia where secondary calcium carbonate has coated the flake, so you'd have a flake of graphite with a skin of calcium carbonate around, which makes it really difficult to extract because it doesn't float properly. And my favorite theme, not all graphite is created equal for the reasons that we've had a look at above there. So, some examples of why they're not equal. If we have a look at the picture on the left, that's a graphite mine in northeastern China, one in Madagascar. Typically, flake graphite is mined from deposits open cast with roughly 5 to 15% graphite. That's the graphite schist or gneiss over there, a granite vein and another graphite vein, schist on the right-hand side, and then the Madagascan deposits are well known. You can see it's a really rusty-looking deposit. It's soft and they can free dig. Then we go underground. As I mentioned, in Germany and Norway, Zimbabwe has a deposit that was mined until last year, typically 20 to 30% graphite. So quite a range in graphite contents. Now this, we don't need to look at all of this writing in the middle here, but I'd really like to highlight the effect of temperature on rocks. If we have a look at this one on the left here, it's slate, which is, we all know, a black fine-grained rock, and you can't see any distinct minerals. Let's say 300 degrees C, then we go up to around 700, and you can see the individual minerals in there. That's just a piece of granite, but it gets the concept across. So temperature is really an important effect, has an important effect on the flake graphite quality and size. Now, how do we look at this lot? I've got some thin sections at the back there if anybody wants to have a look. The rocks are put onto glass and we can look at it through a microscope. Let's have a look at some. So these are really interesting. These are the underground deposits in Europe. And if you bear in mind that these are the graphite flakes, and these are impurities called gangue minerals like titanite, there's amphibole up there, there's pyrite here. The important thing to note is that these are all discrete. The same with that one. So if you crush the rock up, it would be easy to imagine that the graphite would separate from those gangue or waste minerals. So we've called that the good. It's a good benchmark of good stuff. From northeastern China, Heilongjiang province. I said the good and not so good. They're both operating mines. That's got quite nice big flakes. Should be easy to get out. This one over here, maybe not so good. They're a lot smaller, half a millimeter in size, but quite intergrown with other minerals and quite deformed. So and I've got a sample of that rock type at the back there too, if you'd like to look at it later. Then we just happen to have a nice example from Mahenge deposit from Black Rock. You can see nice big long flakes of graphite over 3/4 of a millimeter in length, and again relatively clean edges there that should be easy enough to liberate. Now here's a bad. This one really is a bit of a problem because we've got a lot of mica over there, that brown stuff, that's the graphite. And the mica is a flaky mineral, so that's interleaved with the graphite. It's actually quite difficult because of their physical shape to separate them easily. And now, what I've called the awful. I've got two examples of this. You can have a look at how small the flakes are up there. That's 0.1 of a millimeter scale, so the graphite flakes are less than 50 microns, which is really small, so you'd have to pulverize that rock down to bug dust to extract the little flakes. And there's just another example, and the reason I've showed you these two is these are from two separate continents, probably separated by 10,000 kilometers, but you can see that you can find the same stuff globally if you happen to be in the right geological environment. We might get two populations, which I'd mentioned. Here's a big crystal of a silicate mineral like a feldspar, and lots of tiny little flakes inside it. Then we've got nice big ones over there. I mean, this rock happens to process quite well. But again, you might have a 10% total graphitic carbon in the sample, and maybe 2/10 of that doesn't ever report to the final product. So you've got to be quite wary of the actual grade of the deposit, especially in terms of things like this. And what happens when the graphite is weathered? If we have a look up at the top here, there's clay, and the clay expands when, because it's a hydrous mineral, when the feldspar breaks down, and it'll split up the graphite flakes. So that may, in some cases, cause issues with getting a clean product out, and compare it with that nice solid graphite down at the bottom. So weathering can have an impact, good or bad. Now, why am I showing you this? This isn't a thin section, but what I'm showing you here is reported graphite mineral resources ranked by graphite grade. The one on the left here is less than 2% graphite. All the graphite flakes are jumbo, if you like to call them that. Then we go along the grades through here to end up in that one, which is in Sweden, over 25%, but all of their graphite flakes in that deposit are very, very small. So they're looking at making graphene out of that. So I just want to, you've really got to be very careful. Don't judge a book by its cover, don't judge it by the grade. They're going to have different end products. And if we, here's just a summary of that. Don't be fooled by the grade. 20% graphite in this one, but a bimodal population, but lots of very, very tiny flakes. That one over there, I've zeroed in on the graphite, which is the reason it looks like it's about half graphite, but in reality, the whole sample's roughly 5 to 10% graphite, but nice big flakes. So don't be fooled by the grade. Key conclusions. Variations in original carbon content of the sediment, the metamorphic history, and the weathering all contribute to the flake size and deposits to different extents. Biggest isn't always better. Big tons are nice to have, but don't be fooled by that, and certainly the grade, although as John will tell you, grade really is, if you can have nice grade and nice flakes, you're on a winner. So what matters overall is the quality of the product that we can get out of this rock in the end. And the other important thing is not to forget about is that once the flakes have been extracted and we've got a nice concentrate, what are you going to do with that concentrate? Can you make spherical graphite out of it? Can you make expandable graphite? All important questions to answer. And then the key geological takeaway, very simple, not all flake graphites are created equal. Oh, no, that's my... There was supposed to be a thank you at the end here, but we'll thank you very much. Thank you.